Let's talk now about transfer learning. So in transfer learning, we're going to take advantage of a model that's already been pre-trained and go ahead and retrain that in order to carry out whatever learning task we're interested in. We've seen this quite a bit. So for example, if we are trying to distinguish rhinos from giraffes, we can have a small set of images and then go ahead and use some model that's been pre-trained, let's say on ImageNet. So we take the ImageNet model. So this is an existing neural network. So this could be ResNet, this could be VGG, it could be all sorts of different models. So ResNet, VGG, or some other type of model. And this, of course, could be one of the different flavors of ResNet, ResNet 34, ResNet 101, examples, VGG, different sizes, and so on. This neural network was trained on ImageNet. This is the millions of images with 1,000 different categories. So categories ranging from, let's say, apple all the way to zebra, of which there are 1,000 of them. Now, apple and zebra specifically may or may not be ImageNet categories. I'm not sure. I'm just trying to give the idea that it's A through Z. So we have these various different images. And the way this is normally set up is we have convolutional layers here, and then we have maybe one or two fully connected layers here. So we have fully connected, we have fully connected, and then we have a softmax at the end. All these weights are pre-trained, right? So we have gone through, someone else has gone to the trouble of pre-training this network. So this network is tuned, is designed for taking in images and coming out with one of these 1,000 different categories. What we do is then we repurpose this network and these pre-trained weights. So we go ahead and get rid of this head. So this is the old head of the network. Right? The head is what we talk about as the last part of it, and we repurpose it. So we take the same neural network, except we cut off the head, and then we bolt on a new head. And we've got the output from this portion of it is the same as the output in here. So we've got the same output going in here that we did across here. So we have here the CNN, and we have pre-trained weights. In our new bolt-on head, we have random weights. And now we're going to go ahead and do some training. So we're going to feed in some images. We're going to take advantage of the fact that this is pre-trained, and so we can train with a lot fewer images than, let's say, this original network was trained on. So this initial network was trained on millions of images, millions of training instances. We're going to train on something more like hundreds of instances and get some good results. We feed this in. Before we feed this in, however, it's important that we freeze these weights. All right? So we freeze the pre-trained weights. Why do we freeze those weights? Well, because otherwise, what's going to happen? Oh, and let's look at the output of this new head, right? So it might be something as simple as two outputs, right? Whether it's a giraffe, pardon my spelling, or a rhino, right? So we might have a softmax of two values coming out instead of the 1,000 here. We have a lot fewer weights that we need to train than in the entire network. So the set of weights here is presumably much smaller. We'll have one or two fully connected layers here. But we freeze the pre-trained weights because otherwise, when we go through training, what's going to happen? Let's say we get an image go through here. We've got random weights here. So we're of course needing to be updating these weights, but part of this randomness means it would be sending back some sort of random updates here, very large updates into our pre-trained weight layer. So this would have the effect of messing up many of these weights. So instead we say, let's just live with these weights as they are, and we're going to go ahead and train these random weights. Why do we think this is good? Because we've got all sorts of useful information coming out of this neural network, right? This pre-trained neural network had lots of information, probably, about things that were necessary for doing all this categorization. So we might have information like feathers and wheels, and it knows how to recognize what other things, skin and grass, and lots of different things, lots of patterns, lots of colors, and so on. So it's going to be information that was useful to these last few fully connected layers in order to do this categorization. And we think that's going to be generally useful. Now, is this useful for training all images? Probably not. Let's say you had radiological images, okay, or weather maps. Those might turn out not to be particularly useful, the outputs of here, for training. Now, is it better than a completely untrained network? Maybe. And that might be the case, that you're still getting some advantage because there are some aspects of recognizing visual things where recognizing images out in the world would be useful for also in, let's say, radiological images. So we freeze the pre-trained weights. Okay, that's the first thing we do. And then we go ahead and do some training. What's that going to do? That's going to update these random weights. So we would expect our performance on recognizing giraffes and rhinos would get better and better. These random weights would get better and better and would be tuned to the output of these pre-trained weights. Once we start overfitting, we stop, but there's still something else we can do. And that is, if we think about it, this layer between the pre-trained weights and the new head was predefined by the necessity for the ImageNet categories that we were creating. It may be that there could actually be some fine-tuning that happens, in that perhaps the CNN, we could go ahead and update some of these weights to be better suited for the task at our hand rather than the task of training on ImageNet. So what we can then do is unfreeze the pre-trained weights and train some more. Probably with a lower learning rate. We needed a higher learning rate because we've got all these random weights, and here we're just doing some kind of fine-tuning. So this is in fact what FastAI's fine-tune does. So it goes ahead and freezes the pre-trained weights, does I think 1 or 2 epochs of training, then unfreezes the pre-trained weights and trains some more. If you want to get really good at this, what you would do is you would say, okay, we're going to go ahead and freeze the pre-trained weights and do some training. Then we're going to just unfreeze the last layer of the pre-trained weights and do some training. And then unfreeze the last 2 layers and train, last 3 layers, and so on, so that we can get this successive progression of careful fine-tuning. There is a performance enhancement you can make as far as your training. So if we look at this CNN pre-trained weights, we feed in an image. So let's look in more detail. We go in here, we feed this through the CNN portion. And what does that spit out? That spits out a feature map, right? A set of activations. So this is the output of the pre-trained layers. And then we feed this into our new head. This is happening kind of all automatically because we have created one model, and so it's, of course, for each layer, creating an output, creating an output, creating an output, creating an output, and so on. And that's what's happening here. What I want you to notice is that we go through from epoch to epoch, we're going to be sending, assuming these are frozen, we are going to be, so let's in fact just write that, so these are frozen. We're doing a twofold mapping, right? We're mapping an image into a tensor, and then we're taking that tensor and feeding it through our new head of our neural network. Well, for every epoch, we'll go through and do this conversion from image through the CNN with frozen weights to this tensor. Why not just go ahead and do that one time? So what we can do is run each training instance through the body of our neural network. That is, through here. Save the output activations. And then what we can do is go ahead and train the head and the head only. So we're going to one time go through, create all these tensors. And now what we're going to say is, okay, we have a simple problem. We have a very small neural network with a couple fully connected layers, and we're going to go ahead and feed in our saved, converted output activations, which are these tensors, in through here. Now, I'm assuming somewhere we have a flatten, right? We either have a flatten at the beginning of this head or a flatten at the end of this CNN, one or the other. If the flatten is here, this is not a three-dimensional tensor, right? This is just going to be a flattened activation. But let's assume the flatten is over here. So we've got all these tensors, and these are all the tensors we're going to be training with. And we would expect this training to go really, really fast because this is a very small network. So we don't have to pay the price of going through here. Once we've trained the head, we then could go ahead and go back, unfreeze the CNN pre-trained weights, and then fine-tune. But we'd have to fine-tune with our training images rather than with our saved output activations. So here we're training our head using saved output activations. What are we giving up here? Well, we are giving up the ability to do data augmentation, right? If part of our training process, we go ahead and have some transforms that, let's say, flip training images in order to augment and have extra data, then that works fine as we're feeding through these pre-trained weights. But that won't work well here, unless we go ahead and do data augmentation and come up with a larger collection of outputs here. So we have not only our original outputs, but then we also have data augmented outputs. The problem is, well, the way we normally work, right, is every epoch we're going to do different augmentation for a particular image. So a particular image might one time be flipped and rotated 2 degrees and zoomed in a little bit, and the next time we have different sort of augmentations and so on. So that is the trade-off we have to make. So we either give up on augmentation or we have to do a fixed set of augmentation that we're doing through here and save in a much larger data set. So maybe what we're going to do is we're going to take our original 200 images of giraffes and rhinos and create a large augmented set. Maybe we go from 200 to 2,000. Okay, so now we have a larger set of augmented images, and we go ahead and use that for our training. Right? So the idea then is, we said here, we just train here. Just train this part. That's really it for transfer learning. Well, except the fact that this is not limited to images. So historically, that is more than a couple of years ago, this was routinely used for doing work with images. So working with convolutional neural networks, it was very common to go ahead and take a pre-trained network trained on ImageNet and then go ahead and repurpose it, use it for transfer learning for some other task. However, this was uncommon for doing language work. So if you had texture work, it was uncommon to do something which is done today, which is like take a language model. Okay, so here we'd have a language model with frozen weights, and its old head was used for predicting new words, and repurpose that to do something like sentiment analysis, whether this is positive or negative, or other sorts of tasks. Today, however, that is common. So take this very powerful language model, which knows a lot about language, a lot about words, and go ahead and repurpose that.